So we say that the Laplace transform exists only for those values of sigma for which the Fourier transform of x of t e power minus sigma t exists. Okay. So those set of all values where the Laplace transform exists is referred to as the region of convergence. Okay. And what does it mean? So we have that x of t e power minus sigma t e power minus j omega t dt. So this integral should exist. So now let us say that this integral exists for sigma equal to 0. So if sigma equal to 0, the entire term becomes 1, which means this is the same expression as the Fourier transform expression, right? So whenever the region of convergence has sigma equals 0, then it means for that particular signal, the Fourier transform always exists. So if the region of convergence contains sigma equal to 0, then you can be safe that the Fourier transform exists for that signal, so you can use Fourier transform itself if you want. And how does this ROC look like? So these ROCs are nothing but regions in the S-plane. So remember, what is the S-plane? The S-plane is the complex plane. It is a complex plane denoted by sigma plus j omega. So the ROC is basically the set of all points sigma plus j omega such that x of sigma plus j omega exists. So this is what we refer to as ROC. If the Laplace transform exists for, let us say, 1 plus j omega, which means this belongs to the ROC. So we are worried only about the value of sigma, right? We are not worried about the value of omega. So when sigma is equal to 1, if the Fourier transform exists, that means Laplace transform also exists. Then let us pick sigma equal to 1. Then for all values of omega here, this Laplace transform will exist, because this is only about the absolute integrability in the time domain. It is not anything to do with the frequency values, right? So for all values of omega, this Fourier transform will exist, which means Laplace transform will exist. So that means this entire line, which extends from minus infinity to plus infinity, will be part of the ROC. So now you club in all values of sigma for which this Laplace transform will exist. So let us say for sigma equals 1 to 2, any value that you pick between 1 and 2 in the interval, let us say the Fourier transform will exist, and as a consequence Laplace transform also exists. So let us say this belongs to the ROC. Then we can say that the ROC now will look like, let's say this is 1, this is sigma equals 1, this is sigma equals 2. So any point in between sigma equals 1 and 2, if you pick, this signal will be absolutely integrable, which means Laplace transform will exist. So this entire region, okay, now this entire area is part of the ROC. So ROC is represented by an area in this S-plane. So you take the S-plane and then you shade a region, creating an area, and we say that you pick any point in this region. So let us say I pick this point. So this point is of the form, let us say, a plus jb. So b can be any number from minus infinity to infinity, and a will be any number between 1 and 2. So any point in this region will be of this form. Now if I pick that point and substitute into Laplace transform, that is, try and find out x of a plus jb, or in other words, you just substitute s is equal to a plus jb, then this value will exist. This will exist. Why will it exist? Because how did we compute x of s? We computed this x of s as x of t e power minus at sigma j bt. Basically what I have done is substituted a for sigma and b for omega dt. And because the Fourier transform existed, because this e power minus at was sufficient enough to make this as finite energy, we have this Fourier transform to be existing, which means the Laplace transform will exist. So this is what we refer to as a point in the region of convergence. So you take any point in the region of convergence, substitute in the Laplace transform expression, and if it exists, meaning it is not infinity, okay, or it is not undefined, okay, then we say that the Laplace transform exists in that particular point, okay. So this is what we refer to as region of convergence. Clearly from this discussion we can see that region of convergence can only be strips parallel to this imaginary axis. It cannot have something like this. So you cannot have a small patch where the Laplace transform will converge, because if the Laplace transform converges for this point, then it should also converge for every other frequency above and below it, okay. So it should be strips of lines which are parallel to this imaginary axis. The region of convergence is independent of the value of omega. The only thing that it depends is the value of sigma. So we are picking the values of sigma where the Fourier transform of this term exists, right? So it depends only on sigma and not on omega, and hence ROC should always be strips parallel to the j omega axis. So if some sigma exists in this ROC, then automatically it means that x of t, basically what we have here is, we say that mod x of t e power minus sigma t becomes absolutely integrable, okay. So we are making sure that the signals contain finite energy, or so we are making sure that it is absolutely integrable, and hence for any point in the ROC this is true. So this is the definition of ROC. Basically it is a set of all points where Laplace transform is defined. Now this ROC will contain some important structure when the signal has some structure. For example, if x of t is of finite duration, meaning x of t is equal to 0 for t which is, let us say, not in some interval a to b. What does this mean? It simply means that our x of t looks something like this. That's all. So from a to b it is non-zero, for all other values it is 0. So this is what we refer to as finite duration signal, right? For any signal which is of finite duration, the ROC is the entire S-plane. Why is that? This is because if it is of finite duration, then we can clearly say that this is from A to B, and if x of t is bounded, if x of t is finite duration and bounded, okay, then we can clearly say this is finite. What is the maximum value it can take? Let us say it is bounded by, let us say, some capital M. This is the maximum value it takes. Then what is the maximum value this integration can take? So if the maximum value of the signal is some M, maximum value of this integration is b minus a times m. It cannot be greater than that, which is less than infinity, which means that this signal is already containing a finite energy. So there is a finite energy signal, which means the Fourier transform already exists. So you don't have to do anything, the Fourier transform already exists. Now if you multiply e power minus sigma t with that e power sigma t also is now within a finite interval, right? That e power sigma t. So if sigma is positive, you have a curve like this. If it is negative, you have a curve like this. Whatever it is, it's going to be within a finite interval, which means it is also bounded. So what is the maximum value e power sigma t can take in this interval? It is going to be e power minus sigma a if sigma is positive, or e power minus sigma b if sigma is negative, okay, not more than this. So therefore the signal is bounded no matter what value of sigma you choose, and hence this entire signal which is of finite duration will always end up having an ROC which is the entire S-plane. So if I have to draw the ROC of the entire S-plane by shading, what will I do? I'll just simply shade the entire region, that's it. So the ROC for a finite duration signal which is also bounded is the entire S-plane. Now what if I have a right-sided signal, right? Most causal signals are right-sided. So this is of very special importance to us because most causal signals are right-sided. So what if the signal x of t is right-sided, okay? So if a signal is right-sided, and let us say somebody says that the sigma equals A is in the ROC. So what are they saying? So there is a signal which is right-sided, which means the signal that is given to us looks something like this. Okay, it starts at a particular point and then it goes on the right side. So this is a right-sided signal. Now the claim is that in the S-plane, the ROC contains the point sigma equals A. Sigma equals A means, of course, it's not a point, it's a line. So if this is a line that is present in the ROC, then we can be sure that anything that is to the right of this line will also be in the ROC. Why is that? So if a particular line A is present in the ROC, then what does it mean? It means that this integral x of t e power minus at dt is less than infinity. So this is already an integral which is finite. Now what if we put in a value which is greater than a? In other words, let us pick a point b which is greater than a. So you can write b as some a plus some epsilon. So we can say that integral x of t e power minus bt dt is in fact nothing but minus at times e power minus epsilon t. So we already know that this is a signal which has finite energy. You are only multiplying that with another decaying signal, which means it also has to have finite energy, which means this entire signal which have finite energy. So for a right-sided signal, this makes sense. Why for a right-sided signal alone this makes sense? Because we are starting at some point on the right. So let us say this is C or C to infinity. Because this epsilon is greater than 0, if the signal kept on extending even on the left hand side, then we can have a rising exponential, right? So this exponential can keep rising and we don't know what will happen on the left hand side. Whereas if it is a right sided signal, it will start at a particular point C, which means we know exactly where the exponent starts. So we know the maximum value even on the left hand side. So we know the maximum value, which means it is bounded. So it's not going to go beyond that. So hence, if it is right sided, then we can say that this is true for sure. Otherwise, if it exists on the left side, then the exponent can keep growing on the left hand side without any bounds, and that can make the signal have infinite energy. So for this reason, we need to have a right sided signal. Okay. Now similarly, we can say the same thing for a left sided signal. So what is a left sided signal? It's exactly the same thing whatever we said for the right sided signal, only that now things are on the left side. So a left sided signal will look something like this. The left side or right side is determined about the origin. Okay. So left sided signal can keep extending on the negative values of time, but for the positive values of time, it starts at some C and keeps going on the left side. So this is the left sided signal. Now let us say the ROC of this signal contains a particular point A. So there is a line sigma equals A that is present in the ROC. Then what can we tell about the points on the left or right side? We cannot say anything about the points on the right side, but we can make a comment on the points on the left side. They all will be in the ROC. Why? For the same reason as before. So we said that x of t e power minus at dt is less than infinity for this left-sided integral. So if this is left-sided, then how will this integral look like? So we can replace this integral's limit as integral from minus infinity to c. Okay, from minus infinity to c, you have x of t e power minus at dt to be finite. Now what if you try to find out what happens to some b which is at this point? Okay. Now this b is less than a, which means you can write this b as a minus epsilon. In other words, this signal is x of t e power minus bt, which is e power minus at times e power epsilon t. But note that t is actually going from minus infinity to c, or in other words, you can split this integral to minus infinity to 0 plus 0 to c. So, minus infinity to 0, this exponent is actually decaying. Why? Because epsilon is a positive number, but t is a negative number in this interval. So, this exponent is actually decaying. Because it is decaying, it can only make the energy lesser. It cannot make the energy more. What about this interval? In this interval, this is a finite interval. So, no matter what, whatever in this interval is going to have only finite energy. So, we have split this into two intervals, with one is infinite, the other one is finite. So, according to our previous discussion, anything which has a finite interval, the energy inside that interval is going to be finite. So, this is going to be a finite energy signal in this interval, and in this interval, because t is negative, e power epsilon t will be a decaying signal, and hence the energy in that period will also be finite. As a result, for a left-sided signal, if a is present in the ROC, then any value which is less than a will also be present in the ROC. So, the ROC of a left-sided signal will be left-sided, the ROC of a right-sided signal will also be right-sided. Now, what if a signal extends on both left side and right side infinitely? Then possibly the signal might have an ROC which is bounded, which can look like a rectangular strip, an infinitely extending rectangular strip like this. So, if you see a rectangular strip like this, then it means clearly the signal is not extending infinitely on the right side nor on the left side. So, it cannot be a right-sided signal or a left-sided signal. And clearly the ROC is not the entire S-plane, so it cannot be a finite duration signal. So, the moment you see an ROC which is a rectangular strip like this, you can directly declare that the corresponding time domain signal is extending infinitely from minus infinity to plus infinity. Otherwise, you will never get an ROC like this. So a lot of insights could be obtained just by looking at the ROC, and the time domain signal structure will determine the ROC structure as well. Now, let us see an example. So, x of t is some e power minus at u of t. If you remember this, this is basically the impulse response that we got for an RC circuit. Okay. So, if we try to find out the Laplace transform of this, then x of s is integral minus infinity to infinity e power minus at u of t power minus st dt, which is equal to 0 to infinity e power minus a plus st, which is power minus a plus st divided by a plus s. So, what is this? You just substitute t is equal to infinity here, we get 0, t equal to 0, here we get 1. So, the answer is 1 by a plus s. What is the ROC here? The ROC here depends on the value of s for which this integral actually converges, which means, so we can write this integral as 0 to infinity e power minus a plus st dt as integral 0 to infinity e power minus a plus sigma t e power minus j omega t dt. So, we have to ensure that this a plus sigma t is always positive. Okay. If it is not positive, let us say for some value of sigma, this is negative, then in this interval from 0 to infinity, this can grow unbounded. So, because it can grow unbounded, what happens? We will end up having infinity here, and hence we cannot integrate, and the integral will be undefined. As a result, we will say that this integration will give you a finite value or a defined output only for a plus sigma to be greater than 0. In other words, sigma should be greater than minus a. So, the region of convergence ROC is nothing but the real part of S, which is sigma, should be greater than minus a. That is the region of convergence. So, if you draw it, what would you get? In the S plane, you have sigma j omega. Minus a will be somewhere here if a is positive, or minus a will be somewhere here if a is negative. So, let us say a is positive. So, now this line appears here. So, the region of convergence is now given by all the points which lie to the right of the point minus a, or the line minus a. This also makes sense because if you plot the signal in time domain, this is a right-sided signal, right? So, this is t x of t, this is e power minus at, so it just goes like this. So, this is a right-sided signal, so the ROC is also right-sided. Now, what if we consider another signal which is given here? This is a left-sided signal. How does that look like in the time domain? It looks like minus e power minus at, so the values are negative. The signal looks like this. It keeps growing. Okay. This is 1, and the signal keeps growing in the time domain on the left hand side, okay, because there is a minus. This is a left-sided signal. So, the ROC should also now be left-sided. So, let us see if that is true. So, let us do this computation. In this computation, now the integrals become minus infinity to 0, e power, same thing, everything else is the same. There is a minus here, okay. And now this integration is plus minus infinity to 0. Now you substitute 0 here, you get 1, and you substitute minus infinity, you get 0. So, the interesting thing is, for both these signals, you get the same Laplace transform, that is x of s turns out to be 1 by a plus s for both e power minus at u of t and minus e power minus at u of t. This you would never see in Fourier transform, because for two different signals, Fourier transform will give two different values. But Laplace transform seems to be giving the same value for two different signals. But that is not actually entirely true, because we have found out only the expression. Laplace transform is not defined only by this quantity. You need something more to define Laplace transform, which is the region of convergence. So, just x of s does not define Laplace transform. The region of convergence also is required. So, if we see the region of convergence here, it will be different. So, the same expression x of s can be corresponding to different time domain signals for different regions of convergence. Now, let us see what is the region of convergence here. So, the region of convergence here is minus infinity to 0. Now, we can rewrite this as similarly the same thing. So, for the negative values of time, if t is negative, this integral, basically this expression here, will be bounded only if a plus sigma is less than 0. If this was positive, let us say, if a plus sigma was positive and t here is negative, which cancels out this with negative, then we will get exponent of some positive number, which can grow unbounded in this interval from minus infinity to 0, which means energy can become infinity. So, we want the energy to be finite, meaning this should be a decaying signal, its value should be bounded. So its value can be bounded only if this exponent sigma plus a is negative in this case in this interval. Depending upon the interval, the sign also changes. So earlier the interval was from 0 to infinity, so we wanted a positive value. Now the interval is from minus infinity to 0, so we want a negative value. So which means we are looking for sigma which is less than minus a. In other words, the region of convergence is on the left side of minus a. So earlier it was on the right side of minus a, now it is on the left side of minus a, which makes sense according to the properties that we saw. So this is an interesting example. It reinforces two things. A right-sided signal will have a right-sided ROC, a left-sided signal will have a left-sided ROC, and two signals can have the same Laplace transform expression, but they would differ in their ROCs. Similarly, two signals can have the same ROC, but they can differ in the expression. So you need both this expression and the ROC to completely define the Laplace transform of a signal.